Hey, hi everyone. I hope you're all healthy and well. Thank you for joining us for the next talk in our Golden Webinars in Astrophysics series. As you perhaps know, we have arranged for simultaneous language interpretation provided by Mr. Patricio Gonzalez, Director of Serendipia Soluciones, who will be simultaneously translating for us in both English to Spanish and Spanish to English directions. To avoid confusion with language channels, Ricardo will now give a brief explanation in Spanish as to how to change the language track. However, I believe we're having some technical issues, so you might not see the option yet. Ricardo?
Bienvenidas y bienvenidos todos. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación, que se encuentra en la parte inferior derecha de la ventana del Zoom, y ahí deben seleccionar la opción español. Esto además les permite alternar la pista de audio de la conferencia para poder cambiar entre los idiomas inglés y español. Desafortunadamente, la opción de interpretación en vivo no está disponible para las personas que usan el Zoom en el navegador o en computadores Linux. Les pedimos disculpas por esto. Pronto publicaremos las versiones en inglés y en español de la charla en el canal de YouTube de Astrofísica UC. También sabemos que algunos participantes han tenido dificultades para silenciar la pista de sonido original al escuchar la traducción al español. Esto se trataría de un error en Zoom y la solución es salir y volver a entrar al seminario web. Con ello deberían poder arreglar el problema.
Hello, my name is Thomas Frisia. I'm a faculty member at the Institute of Astrophysics of Pontificia Universidad Católica and the head of outreach. And together with Evelyn Johnston, one of our postdoctoral fellows, we are and will be organizing this series of talks for you for as long as we can. Thank you so much for all your feedback and comments and great suggestions. We really appreciate your encouragement and support. If you would like to support the series, please send us an email, which you will find in your registration. If you like these talks, please also share them with your friends and colleagues. It really supports our channel. We will continue to bring you these talks in the original English and simultaneous Spanish translation. This has been made possible by the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym. Our talk today will be given by Sarah Seger from the Massachusetts Institute of Technology. First though, we will give a brief introduction of how the webinar will run.
If you have any questions during the talk, please type them into the Q&A window. All viewers will be able to upvote questions and comment on them, and we have a team of astronomers and journalists behind the scenes who will be monitoring your questions and will select the best questions for the discussion after the talk. The talk is expected to last around 45 minutes, and we'll have time for questions at the end, and these questions will only be selected from the Q&A window, not from the live stream on YouTube. So before we begin, I'd like to briefly introduce our other panel members. So in addition to Sarah, Patricio, myself, and Thomas, we have Hernan Quintana, who is a professor emeritus at the Institute of Astrophysics at PUC. From amongst our students and postdocs at PUC, we have Carolina Senzano, Sergio Best, Melissa Hobson, Maria Paula Dranco, and Paul Eigenthaler. We also have the pleasure to welcome our guest panelists today. We have Katerina Kravchenko, who is a postdoctoral fellow at the European Southern Observatory here in Chile. We have Surinkana Rukti, who is a postdoctoral fellow at the Center for Astrophysics at the Harvard College Observatory. We have Konrad Tristram, an astronomer at the European Southern Observatory here in Chile. Dennis Crabtree, a director emeritus at the Dominion Astrophysical Observatory and the Hertzberg Astronomy and Astrophysics Institute of the National Research Council of Canada. And finally, we have John Carpenter, who is an observatory scientist at the Joint ALMA Observatory here in Chile. Finally, as usual, we have our excellent team of Q&A managers, Ricardo Acevedo, Daniela Fernandez, and Carol Rojas.
So it is our great pleasure to introduce Sarah Seger as our speaker today. Sarah started her career with a degree in math and physics at the University of Toronto in Canada, before moving to Harvard for her PhD, which she completed in 1999. The first reports of exoplanet detection started appearing in the mid-90s, and so Sarah chose to focus on this area of research for her PhD thesis. She then moved to the Institute for Advanced Study in Princeton as a Keck Fellow before moving on to the Carnegie Institution of Washington as a member of the research staff. In 2007, she was appointed a professor of physics at MIT in Cambridge, which is a position she still holds today as the class of 1941 professor of planetary science. Her previous research has been credited with laying the foundations for the field of exoplanet atmospheres, and her current research has expanded on this topic to focus on the future search for signs of life by way of atmospheric biosignature gases.
She is a member of a number of space-based exoplanet searches and was until recently the Deputy Science Director of the MIT-led NASA mission TESS. She is the PI for the on-orbit JPL MIT CubeSat called Asteria, and is the lead for the Starshade Rendezvous mission. Sarah has received many awards and distinctions throughout her career so far, including an honorary PhD from the University of British Columbia in 2015, and in 2012 she was recognized by Time magazine as one of the 25 most influential people in space. And now we'd like to hand over to Sarah to tell us about her work on mapping the nearest stars for habitable or inhabited worlds.
Thank you so much, everybody. A few billion years ago, the humble cyanobacteria did something absolutely incredible. They figured out photosynthesis, how to harness the sun's light for energy. And in the process, cyanobacteria generated oxygen. So much oxygen that was actually poisonous to a lot of the life forms around it. And cyanobacteria ended up re-engineering the atmosphere. Because without them, or without plants today, and without photosynthetic bacteria, our Earth would have virtually no oxygen. So if there is a star, if there is a nearby star with a planet around it that has intelligent aliens, and if those aliens have the kind of space telescopes we're hoping to build, and they see our Earth with oxygen, they'll know something's very suspicious. Because oxygen is a very reactive gas. and it shouldn't be in our atmosphere at all. Yet it is there to 20% by volume. We call oxygen a biosignature gas. And in the best case scenario, we will be so lucky to find a planet like Earth with water oceans. Liquid water is needed for all life as we know it. And with a gas like oxygen in the atmosphere that we can identify as not really being likely to be created by anything other than life. And that's what we're hoping to do. Only, and those of you who follow the field of exoplanets, you'll know we not only haven't found another Earth-like planet, but we haven't really found any solar system copies. Our solar system is very hard to find. What we have found are so many planets. And in this diagram, I am showing you planet size, going from 1 Earth radius to 10 Earth radii and greater. And on the bottom, and this is on a logarithmic scale. And on the bottom axis, I'm showing you the semi-major axis, the separation the planet has from the star. And what you see is so many planets. Each point is a different planet, actually. And this isn't even all of them, actually, but there's so many, and each color and symbol is a different technique to find planets. So what I want you to see is not just that there are so many planets, but they're all over the place. There are big, hot Jupiter-sized planets very close to their star. There are also these so-called hot super-Earths, some planets that have a period, the time it takes to go around the star, of less than 1 day. And their surfaces are so hot enough to melt rock. So these hot super-Earths might have liquid lava surfaces, not from volcanoes, but from just the heat from their sun. And there are planets here. If you look at this diagram, you might be able to see that it's highly populated right in this clump here, around 2 to 3 times the size of Earth, which we think now is the most common type of planet in our galaxy. But there's no known solar system counterpart. And we don't really know what these so-called mini Neptunes are. We have a lot of ideas, but nothing's really proven. By the way, just for my astronomy colleagues, don't try to read too much into this plot. There are a lot of selection effects in the way that we find planets today. And I also had to do a little fudging because this is showing you planet size. And many of the planets, like from radial velocity, I had to convert from mass to size. And these ones out here, they're converted from brightness to size. So don't read too much into this plot right now. One of the 2 takeaways is that the dark parts of the diagram are where our techniques can't reach yet. We can't reach down to small planets that are far from the star. We're not there yet. But my favorite takeaway is from this planet, because planets come in all sizes and masses and orbits, it turns out, that in exoplanets, anything is possible under the laws of physics and chemistry. Now, it turns out that any planet finding technique we have today, Earth and Venus would look the same because they're about the same mass. Earth and Venus are about the same size. And ultimately, we need to study planet atmospheres because our own Earth's atmosphere is very different from Venus's. We like to know something about the surface temperature, the greenhouse gases, and things like that. In this next plot, and it's the same plot, but the white circles are planets that have atmospheres that have been studied. Not necessarily a detection, just that we have studied. And if you look at the spread of those white circles, you can see we're even further from getting an atmosphere of a planet in this Earth vicinity here, where Earth would be here at 1 Earth size and 1 semi-major axis. So atmospheres, our studies are key, but we have a long, long way to go. So these exoplanets we're finding so far that our techniques allow us to, they're incredibly different from Earth. And we have to also recognize that on our planet Earth, oxygen was only here in large quantities for about half of Earth's lifetime. So in the search for life on other worlds by way of gases in the atmosphere, we really want to ask what kind of gases might be produced by life on another world. Well, I've been thought hard about this problem, and many years ago, I came up with a crazy theory. We're going to come back to this later in the talk, but just for now, think to yourself, how many of you have received emails with crazy theories? Maybe you've even sent one. Well, my crazy theory, when I started out on this problem, really knowing almost not very much about chemistry except undergraduate level, was that I thought that life might make all molecules, all small molecules that are in gas form on a planet atmosphere. And it seemed really logical to me. Supporting my theory was the point that on Earth's atmosphere, every gas that's present in our atmosphere to the part per trillion level, except for the noble gases, all of these gases, they're actually made by life, although most of them have a dominant source other than life. So all the molecules I could think of, like oxygen and carbon dioxide and hydrogen chloride, even like ethane, these gases are actually all made by life. Even ozone is actually made inside some cells. I really like my theory, and it actually turns out to be totally wrong, but I'm going to come back to that later in my talk. And you can mull this over for yourself if you can think of a gas. You may not, because we're all astronomers or astronomy buffs. Any gas you can think of, honestly, it might well be made by life on Earth at least. So that actually completes my introduction. An exoplanet is a planet orbiting a nearby star. We know of thousands of exoplanets right now. It's far in the future to find that true Earth twin, but that doesn't stop us from thinking about gases that might be produced by life that could accumulate in a planet atmosphere. So this is what I'm going to talk about today. But before I get onto that, I want to tell you that I am offering a prize for the best question. So you'll ask your question, and at the end, we'll announce who will get the prize. This prize actually is my memoir, which just came out a couple of weeks ago. And this memoir, it's both personal and professional about my journey through the birth of exoplanets and exploration of outer space. But it's also about inner space as well. So if you don't want to hear about my personal life, then don't ask the best question. This book will be, actually it's coming out in Spanish in the spring of 2021 in Spain. This copy is actually in English. So please, I know you're going to ask a lot of questions anyway, and I know you're going to ask some great questions. So I'm looking forward to answering some of those questions at the end of the talk. So for the next part of my talk, I'm going to walk you through how astronomers we are planning to find and identify a habitable planet that might have signs of life on it. So I have a question for you, actually. And we have a poll. Could you please launch the poll to go along with this? Imagine for a moment you get to switch fields or join professional astronomers. You're going to set out to find another Earth, that true Earth twin. Well, it's very hard to do because our Earth is 100 times smaller than our sun. It is 300,000 times less massive. And our Earth is 10 billion times fainter than our sun. So you can only select one, and I'd like to know, which method would you choose? Would you vote for a method that is planet size, mass, or I'm surprised by, I can see the poll results. So look, if you're building something at home, like my husband last year built a deck, a small deck on our back porch. Do you think he measured, how many decimal places do you think he measured what he cut to? I mean, he did a really nice job, but I don't think he measured to 2 decimal places, which would be planet size. He certainly did not measure to 10 decimal places. So if you're going to vote for number 3, you want to find Earth in its reflected light near its star, you're going to have to build something that's accurate to 10 decimal places, okay? Now, what I forgot to say was that an Earth shouldn't be so hard to find on its own. The problem is the Earth is next to a big, bright, massive star. We can't separate that Earth from its star, not easily. So all of the techniques we have to deal with that star. And that's why it's so hard, actually. Now, some people like to take the easy way out, which turns out, now I'm not going to judge you on your answer, but I will tell you that number 3 is my personal favorite, which we'll get to. But number 1 is the way that we're all finding most of the planets today. So I think we can end the poll. Let's see what the top vote came in. Wow, this is amazing. So it turns out that only the smallest number voted for the easiest way. So you're definitely a great audience. You want to do something hard. Good for you. All right, so we can get rid of that poll now. And I'm going to move on to tell you about the different ways we find planets. Well, the size method is the way we do it. And just in case people aren't familiar with it, we call it the transit technique. And what you see here on the top is an artist's conception, because we don't have any images of a star other than the sun that look like that. And can you see the Earth-sized planet going in front of the fake star, fake sun-like star? What we do is what you see at the bottom. We measure the brightness of stars as a function of time. And when the planet goes in front of the star, we measure a drop in starlight, a tiny drop in starlight. And when that planet finishes transiting the starlight more or less goes back to normal. And on the MIT-led NASA mission TESS, we have this, honestly, work has been going on for a decade or 2 decades. We have it down to what I like to call standard operating procedure. There are computer codes that already exist. We have our own, of course. NASA has their own, and we measure the brightness of 20,000 stars at 2-minute cadence and hundreds of thousands of stars at 30-minute cadence every single month that TESS observes a field for 1 month. And out of all of that, after lots of hard computer time and human beings getting in at the end to look at the planet candidates, we find about 100 new planet candidates a month. I love to imagine those intelligent aliens also sitting around in a room, looking at what the computer spit out. They might see a small drop in brightness and say, imagine if that was our Earth transiting our sun, and say, nah, that signal's not good enough. And that our Earth signal would be tossed in the trash. Now, there's something else about these transits. And some of my slides will be a little complex, but you don't have to understand all those details to understand the rest of the talk. It's for astronomers. I wanted to remind you, well, for all of you, the picture on the left is showing you an artist's conception, that when the planet is in front of the star, it's showing you this fake atmosphere that's glowing. Well, some of the starlight will shine through the atmosphere. And believe it or not, we can observe that. And if we look at the star by itself, and then we look at the star with the planet in front of it, we actually can discern, we can pick out features in the planet atmosphere. Like shining a flashlight through a fog, not all the light will make it through. So there's a little bit of a complicated concept, but I want you to just think about this for a moment. We can imagine looking at the planet at a wavelength where the atmosphere has no absorber. The atmosphere would be, if you will, fully transparent. And the planet will just be a certain size. It'll be the size of its, rocky body. But now imagine a very strong absorber, like a skunk smell, just a tiny bit of some gas that's very potent. And this gas absorbs so strongly that light from the star cannot make it through the atmosphere. Then the planet will look a tiny bit bigger. So what we're doing is we measure the size of the planet, which is equivalent to how deep that transit is. And we do that as a function of wavelength. Okay, so that's a bit tricky, but that is in a nutshell how we study planet atmospheres today. Here is an example for you, showing you transit depth. So this is the size of the planet, if you will. And it's actually the area, but let's just call it this planet size. And this is the wavelength in microns. Now look at this here. There's a giant spectral feature here. And this means the planet looks a tiny bit bigger at a wavelength of 1.4 microns than it does at other wavelengths. So all you have to do to agree that we've detected a planet atmosphere here is to agree with me that the white points are different from a straight line. Okay, if there was no atmosphere on this planet or no spectral features, then in fact, this would just be a straight line. Now these points, just look at the white points, they are points from the Hubble Space Telescope. And the colored curves are models, and you can ignore the left part of this graph. What this feature is, it's actually water vapor. And this is a hot giant planet where we have detected water vapor in the planet. Here's another one. This is also Hubble data. The white points are Hubble data and the colors are models. And this is showing you the transit depth. This is the planet size with respect to its star size. And this is wavelength in microns. And this atmosphere is it's small, but it's relatively big for planets. This is what planet we call a hot Saturn. And again, here's this very giant water vapor feature. And again, hopefully you'll agree with me that this is different from a straight line. Now, I hope you like this image. This is one of our very best atmospheric spectra in all of exoplanets. So sometimes I'll show these plots to people working in another field of astronomy, and they're like, wow, like this is just, what is this? Because look how this data is quite noisy. It's kind of all over the place, although this is significant. This is a gas, atomic sodium, that is present in this atmosphere. And you can look at it from different angles, and you can say, well, those are only 1 sigma error bars. Maybe it's not that statistically significant, but it kind of is, actually. So today, this feature here, if you had time to read the graph, it's a small feature. It's like basically a part in 1,000. So to study this exoplanet atmosphere, you'd have to measure it to a part in 1,000, basically, which is tricky because the raw data is incredibly messy. So today we use the Hubble Space Telescope to study hot planet atmospheres. And we can only study largely giant planets. We have a couple of small planets, but giant planets, we don't think they can host life. They are big, and they are hot, and they have no solid surface as we know it. Jupiter, for example, if you could travel down through Jupiter's atmosphere, it gets hot very quickly, and life couldn't actually survive there. Now, in the near future, soon we will use the James Webb Space Telescope to push down to small, rocky exoplanet atmospheres. So the James Webb is way bigger than Hubble. It is going to orbit at the Earth-Sun L2, 1 million miles away from Earth, where the environment is much better for astronomy. And the James Webb operates in infrared wavelengths, which are very good for finding molecules in planet atmospheres. And honestly, there's probably hundreds of people who want to do this very problem, hundreds of astronomers who want to use the James Webb Telescope to try to find signs of life on an exoplanet atmosphere. And we'll come back to that a bit later. If you look in the bottom right, that's not an appendage of the James Webb. That's actually an illustration of the TESS mission. And we sometimes joke that TESS is the finder scope for the James Webb, because TESS is busy finding small planets right now. And we're trying to find a catalog, like a telephone book of addresses of planets that are good candidates for James Webb. So there's a little more to the story right now. If you pick the 1 in 100 planet size, that was I gave you a little bit of a misleading statement, because that drop in brightness on the transit light curve, it's actually an area ratio. So we have to square it. Instead of 1 in 100, the drop in brightness due to an Earth is 1 part in 10,000. And Earth's atmosphere, it's so thin, it's like the skin of an onion on an onion. And that thin atmosphere projected on the whole star, sun-like star, the atmosphere signal would only be 1 part in 50 million. That's insane. That's very hard. So with the James Webb Space Telescope, we're not going to be measuring other Earth atmospheres. It's way too hard. Instead, we are going to be measuring atmospheres of small planets transiting small stars. And on the right side there, you see a little tiny star. This is a star called TRAPPIST-1. It is so small and so cold, any smaller and colder, it wouldn't be a star. It wouldn't be able to have fusion in its interior. And look how much more favorable that is. I wrote the number down for you. The drop in brightness for the transit itself is 1 part in 100. The atmosphere would be about 1 part in 10,000. And I showed you the so-called beautiful spectrum of the hot Saturn. That was 1 part in 1,000. So we only have to do 10 times better, but we'll have the James Webb Space Telescope, which arguably will do hopefully better than 10 times better than Hubble. Now these planets orbiting these M-dwarf stars, they're quite different from Earth, actually. And to explain that, I wanted to take you on a journey to a planet orbiting an M-dwarf star. Imagine we could travel there in our spaceship. We might find, depending on the planet-star configuration, that the star or the sun is very big in the sky. This artist made the atmosphere a different color, just for variety. It could well be. You can see in this particular planet, there's some other planets in this system that's illustrated here, showing you other planets in the same system. Now, a planet orbiting an M-dwarf star that is the right temperature for life will be quite close to the star. That's why the star or the sun would appear so big in the sky, because the small stars give off very little energy. It'd be like having a very small fire. If you want to stay warm, you have to stand very close to the fire. So being so close to the star, there's very strong tides, tidal interaction with the planet and star. And just like, you know how our moon raises tides on Earth, on the sea, on the ocean, we get tides, and our Earth raises tides on the moon. And our Earth actually forced our moon into that special configuration where the moon rotates one time for every time it orbits. You know how you only see the same, almost the same face of the moon at all times? Yeah, that's because the moon it's rotating one time for every time it orbits. We call that tidally locked. It's locked into place. Well, these planets around the M-dwarf star, they would be so close to their star that they're also tidally locked, as far as physics tells us. What that means is that one side is always in daytime, one side is always heated in daytime, the other side is always in darkness. So visiting this planet, we could choose. Where would you visit? Where it's always day? No, because you're an astronomer. You would visit where it's always night, where your telescopes could work. Or, you know, if it was me, honestly, I would go to where the sun is always setting to try to see the green flash phenomena. I'd like to just see that kind of last indefinitely. Now, once I gave this analogy at a conference and someone got mad at me after, a dynamicist, because you may know our moon librates. It's not perfect. It doesn't actually perfectly tidally lock. You actually see a little more than half of the moon. Sometimes it's right at you, sometimes it's like that. So it wouldn't all be perfectly sun always setting, but it would be close. Now, being so close to the star, the planet would, by Kepler's third law, the planet orbits the star fairly quickly. So a year would go by in 10 days. Not sure if there's any kids in the audience. That means your birthday would be every 10 days. Now, on second thought, visiting a planet orbiting an M-dwarf star might not be such a great idea because the stars give off flares. Most of these M-dwarf stars, lots of high energy flares. So we couldn't be glued to our phones because those high energy particles would knock out the electronics on your phone, destroying it. What kind of sunscreen would you bring? We'd probably have to hunker down in a cave somewhere. That wouldn't be fun. So I don't know if any of you have heard of the Carrington event, but just briefly, in the 1850s, a giant flare came off of our sun, but people didn't quite understand at the time because they were just studying sunspots and Maxwell's equations hadn't yet been articulated. What happened was our Earth lit up. It turns out that people could see the northern and southern lights almost to the equator. You could read by it if you were in a relatively northern latitude. We didn't have a power grid back then, but the telegraph operators, some of the wires caught fire. And what had happened was our sun had a giant coronal mass ejection. And part of the sun with a magnetic field embedded in it came hurtling towards Earth. And when that sun hit part of our sun, that had its own magnetic field embedded in it, hit our magnetic field, it induced a current. So let's just keep our fingers crossed that's not going to happen anytime soon. I don't know about you folks in Chile, but here in the USA, our power grid would just get shocked out of existence. Everything would go dark. Now, Patricio and I, we're from Canada, as is one of our guests. We're good in Canada because in the late 1980s, we had a miniature event. I don't know if you remember that. In Quebec, like all the power went out for a while. So they have the equivalent of circuit breakers. So I hope that exists in other parts of the world. Anyway, the point is that that's not good at all. But the TRAPPIST-1 system, here is the beautiful TRAPPIST-1 system in transit data. It's got 7 planets around it. You know that little small star I showed you? Well, it turns out that astronomers have observed it for an 80-day period. And TRAPPIST-1 showed 40 flares. And out of one of those flares, we have to extrapolate because the data was at infrared wavelengths. But, you know, if you see a big flare in the infrared, it's even way bigger. It's got to be way bigger at high energies where the damage happens. And one of those flares the astronomers computed was analogous to Earth's Carrington event. So if we were visiting TRAPPIST-1 as an example, we wouldn't want to, because you don't want to be in the line of fire of a giant flare event that will just basically, who knows what kind of damage it might do. So I told you that story. I'm somewhat biased towards Earth-like planets around sun-like stars. So I just wanted to share that, you know, we were doing the easiest thing we can right now because it's all we really can. It might not be the best thing. So to summarize this part of my talk, in the search for life, we have transits. We have the James Webb Space Telescope, where atmospheres to us are accessible for planets transiting M dwarf stars, small planets transiting small stars. And we already have the TRAPPIST-1 planets. We have a few others as well. So we're ready to go in a search for habitable worlds with the transit technique. But transits are only the first part of a long story because they're limited to a fortuitous alignment. As planet star rotation axes are all randomly distributed, so for example, if that planet is orbiting the star in the plane of the sky, it will never show a transit. So most planets actually do not transit. We can find so many because we're just looking at tens of thousands, hundreds of thousands, millions of stars, and the numbers work out in our favor. But if we want to find planets nearby, and we want to work on that 1 in 10 billion problem, we can't wait for transits. We have to do another technique. We call it direct imaging. We need to block out the starlight so we can see planets directly. Now, this could be a device inside our telescope. We call it a coronagraph. There's lots of coronagraphs out there. Or this could be a different one. We'll get to that in a moment. An external occulter, like a giant screen in space. So I'm going to just walk you through this plot that shows you where we are and where we're trying to go. This plot is showing you the flux ratio to the host star. So if you voted for number 3, you want to keep your eye out down here at the 10 to the minus 10, the 1 part in 10 billion level. That's where Earth is. If we're imagining we want to do direct imaging and block out the starlight to 1 part in 10 billion, we have to be down here on the diagram. And this is the separation. We have it in arc seconds. So as projected on the sky, it's easier to find objects that are far from the star. It's hard to see objects that are very close to the star. These are estimates, or actually, these are curves showing you what we have with some of our current telescopes or planned telescopes today. We have Gemini GPI, we have VLT Sphere, Hubble. And up here, I'm showing you in squares the planets we have today. This is where we're at today, right now. We're only at this top part of the diagram. So I'd like to ask you, in your job, whether you're an astronomer or another job, who has to go so many orders of magnitude? We've got to go from like a few 100,000 down to 10 billion. And we have to go from, this separation's harder than it seems. We've got to go from a few arc seconds down to a fraction of an arc second. Or we have to go down to, let's say, 100 milliarc seconds or better. That's where we're at right now. With the ground-based telescopes, we have GPI, we have Sphere. As a little aside for astronomers, so in exoplanets, we're usually very lucky. There's so many planets. You find one, and then you find many. The only field where there's been a scarcity of planets, unfortunately, has been this area of direct imaging. When we were hoping that GPI and VLT Sphere would find dozens of planets, they didn't find very many, actually. It may just be that planets can't form easily that far from the star. We have large ground-based telescopes under construction. The 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope. These telescopes will get us down to this level here. I put a giant, and they will actually do direct imaging for M dwarf stars in reflected light. I put a big P there for Proxima Centauri. Our very nearest star appears to have an Earth-mass planet in its habitable zone. And we will be able to get a look at its atmosphere with the right instrumentation. We actually do require extreme adaptive optics. And there's this sort of new movement afoot I just thought I'd share with you in case you hadn't heard of it. But there are people, there's 2 groups. One is Professor Carrie Cohoy at MIT, and a separate group is Dr. John Mather, this former Nobel laureate for the COBE. They are each working on, and maybe there's another group, a laser guide star that would actually be in outer space, that would shine down onto your telescope to make like extreme adaptive optics. Because the reason we're stuck here, we can't go down to 1 part in 10 billion, is that we don't have a bright enough laser guide star. We have to sense the atmosphere and control it to get rid of the blurring effects of Earth's atmosphere. And we couldn't really do that on the ground. We have to construct such a giant laser that it would cost billions of dollars and be incredibly powerful. It just wouldn't make any sense. Now, if you voted for number 3, we're working on that right now. And my favorite project is, we call it, I'll show you what the star shade is in a moment, but it'll get us down here and we'll be able to study the nearest stars. We can study the nearest 6 or 12 stars or so. It'll be great. But in the last few years, NASA had put in money to do a study. All right, and here let me just say that it's now called the Roman telescope, but our idea would be to rendezvous, which is meet up, to launch a giant external screen that would meet up with the space telescope, namely Roman telescope. This plan is not going quite as well as we had hoped because we always have budget problems. And until recently, the Roman telescope was, it had to be starshade ready. So they didn't make any decisions that would make it not work with the starshade. You know, that's slowly been changing. And so we're waiting for the United States Decadal Survey to hopefully come back and say something great about Starshade Rendezvous so we can get back on track to be able to go with the WFIRST telescope. But don't worry, we always have more plans. And there's these more powerful starlight suppression missions under study. Actually, the studies are now completed. We have HabEx, which is a 4-meter space telescope that would work at visible and very near infrared wavelengths. Would have an internal coronagraph and an external starshade. And there's a concept called LUVOIR, where they have an 8-meter and a 15-meter. That's pretty much as big as you can make it and still fit in a rocket fairing that exists or will exist. And just in case anybody's interested, I'll let you skim some of those details of the HabEx Observatory. I was community co-chair on that study. It's incredible. These studies, they go on for 2 or 3 years. There's lots of astronomers. There are lots of engineers. It's not like a mission you can go and build tomorrow, but the goal is to show the design closes and to give it a cost and risk assessment. And it's costly. You can ask me. You won't win the prize for the best question if you ask me how much it costs, but I will answer it for you. So Starshade could launch with the telescope and separate on orbit. It would have these giant petals that will have stowed, and they will expand to their position. Starshade is a giant specially shaped screen. It would be tens of meters in diameter, and it would formation fly tens of thousands of kilometers from a space telescope. The starshade has to be made incredibly precisely because it has to be able to block out that starlight to 1 part in 10 billion. I'm going to play that movie again for you. Starshade was first thought of in the 1960s by Lyman Spitzer, who also conceived of the Hubble Space Telescope. He actually worked out all the math. We don't think it could work with Hubble for a lot of different reasons. But anyway, Starshade, he worked out the math for it. And Starshade was revisited each decade since the 1960s. And finally, about 10 years ago, I got asked to lead a study with a large part of the community. And we were able to tie all the engineering and all the science studies together and make Starshade to be considered like a real possibility, a real tool for astronomers. Starshade has to be this very special shape because it's got to block out the starlight to avoid diffraction. I'm going to let you, let's see. I'll answer that in a second, but I just want to show you this picture of myself and some team members. This is showing you a petal prototype. It's big. Remember I said it's tens of meters in diameter? The petal could be 5 meters or 10 meters long, depending on the 5 meters or 8 meters long, depending on the design. This petal was used for manufacturing tolerance verification tests, meaning the petal has to be a shape to within about 100 microns. And the team had to demonstrate that we could make a starshade petal that actually matched what it has to be. So you could fabricate it to the width of the human hair, if you will. Here's a nice picture of the Starshade Lab at NASA Jet Propulsion Laboratory, showing you a variety of scale models. So I want to make sure I stay on time here. So I'll briefly tell you why Starshade has to be a special shape. You might imagine putting up a circle in space or a square, which would be a lot easier to build and manufacture and probably deploy. But the problem is, if you were to block out a star with a big circular screen, you actually wouldn't be blocking it. Instead of blocking out the star, you would actually get an image of circles, contours, light on your image. And that's because the star can act like a wave, light can act like a wave. And the starlight would bend around the circular screen edges. An analogy is like dropping a pebble in a pond. You would see ripples. And blocking out that star with a circular square screen, you will see ripples of light. And those ripples of light are like 100,000 times brighter than the planet you'd be looking for. So if we make the star shade a very special shape, which is determined mathematically, by the way, then star shade will block out the starlight. It would be like the starlight can diffract around the edges and interfere with itself. It would be like dropping a pebble in a pond. But instead of seeing ripples, the pond would be perfectly smooth to 1 part in 10 billion. And all the waves, all the ripples would be pushed to the outer edges. So to summarize this part of my talk, we also have direct imaging to search for life. We have the large ground-based telescopes now under construction. They can survey a few dozen M-dwarf stars. And the good news is we have more than one, but our favorite one is Proxima Centauri b, a planet around the very nearest star. Now, we more or less require going to space to find the true Earth twin orbiting a sun-like star. And I briefly gave you this overview of a range of mission options. So now for my favorite part of the talk, about signs of life research at the frontier. So the problem we're facing is we're very, what we call Terra-centric. You know, we're all biased and there's all this diversity, conversation around diversity. Well, with these planets, we're just so biased to Earth. We can barely imagine other worlds that are so different. But we know they have to be because there are different masses and sizes. And we have no idea why our Earth's atmosphere is the mass it is, or even in most cases, the composition. So we're expecting things to be different. And I've been guided by this quote I found a number of years ago. Nothing would be more tragic in the exploration of space to encounter alien life and fail to recognize it. And what this means is that if we're trying to find life in our traditional astronomy way, by looking for gases on a planet far away, we don't want to miss that. And so I've now dedicated this part of my career to searching through all these molecules. And here's where I get back to the crazy theory. So I would like to know how many of you, I'm ready for poll number 2 now, how many of you have received a crazy theory? Usually it's physics. Someone has an explanation for gravity or wants to explain where the electron came from. And these theories are usually, you know, from someone who just doesn't have the right background in physics. And there was me with my theory in chemistry. Yeah, and if you sent a crazy theory, and by the way, please don't send me your crazy theory. I'm just surprised how many people have sent a crazy theory. Okay, Thomas, now you know who's writing to you. Well, it is an anonymous poll. So the question about the crazy theory, remember my theory was that life produces all small molecules. Who does the MIT professor go to with a crazy theory? Like I could go to Thomas, for example, but he might not be able to help, especially because it's a chemistry problem. Well, I roped in my 2 biochemist colleagues to work on this theory. And we found a Nobel laureate to go talk to. His name's Jack Szostak. He works at Harvard, which is close to MIT. And we brought our theory to him in the form of a presentation. We went on the subway across the river to Harvard MGH. It's like the medical school. And he shot down that theory in like less than 5 minutes because he found a counterexample, a molecule that's a small molecule that's not produced by life. Well, I was personally a bit crushed. My biochemist colleagues, they didn't really believe in the theory. They just kind of did it with me. But we went back to work and I wrote a combinatorics code where I could put together basically all molecules made of the big 6 elements, carbon, nitrogen, oxygen, phosphorus, sulfur, and made a scaffold of those of like 6 atoms or less, and then populated it with hydrogen atoms. Now, there were thousands of molecules. I got like a list of 27,000 molecules because although some combinatoric you could make, it wasn't a real molecule. Other ones, for the same formula, you could have lots and lots of different structures. Then we, mostly my biochemist colleague, Janusz Petkowski, literally trolled the literature. We also had a really good Chinese grad student who was able to scrape this database that was only in Chinese, and we scraped a lot of databases. And we put together really 3 separate, very long lists of things. All molecules that can be in gas phase, at room temperature and pressure, and we also had a database of all molecules produced by life. Okay, so the poll's pretty good. It's what I wasn't expecting that many people to have sent the crazy theory, but nice work, everybody. And I would have had to fill out both of those. Okay, I think we can stop sharing the poll now. All right, so we actually had a good time in this, we call it chemoinformatics. And it was incredible, but we started with this, imagine a sea of molecules, which we call filling chemical space. And our algorithms are like this shaker filter. We're able to sort all the molecules into different categories. And we found some amazing things actually, which I don't totally have time to talk about it all, but we did sort of find that there are some molecules that are rarely or they're never produced by life, ever. And we actually started working through each of these. It's not necessarily a molecule, but a fragment of a molecule that we call chemical motif. And we found that some bonds or some fragments are just never produced, and we started working through them. We've only got through one so far. A nitrogen-sulfur bond, it turns out, life very rarely makes. And yeah, we started to explore why. And we think we found a reason for that first one anyway. We also, and that's the stream on the left. Those are molecules that are not made by any kind of life on Earth. In this image, we also show two other streams that are molecules that might be relevant for life on Earth. And in my team, it sounds quite overly ambitious, but we aim to go through all those molecules produced by life. There's a lot of them. Like when you think about molecules made by life, think about if in your fridge you have something that went moldy, that really bad smell, that's a molecule being made by life. Or if you walk in the pine forest and all those good smells coming off the trees, those are molecules made by life. And it turns out life on Earth makes thousands of gases, actually. We, in this combinatoric search, we found like 14,000 gases or more that are molecules that are gassed at room temperature and pressure, and about a quarter of those are made by life. Now, I only have one of them to tell you about, actually, in the interest of time. But I was first going to blast through a couple of things for my astronomer colleagues, because I wanted you to know a bit about what's going on in atmospheres. So we work on atmospheres of exoplanets. Mostly we're limited to one dimension for making our spectra. But essentially, it's a complicated problem because of photochemistry. So, in astronomy, we're often trained to study stars and how rate of transfer, how photons transport energy, and how you can generate spectral features in a stellar photosphere. But on the planet atmosphere, we have gases coming out of the surface. I called it geoflux or bioflux. And the problem is that photochemistry is very complex. And for atmospheres different from Earth, we might not even have reaction rates that exist. Now, there's another thing going on in exoplanets I wanted you to know about, and that is we have a thing called exoplanet retrieval, which actually my students and we were some of the first to ever work on this for exoplanets. And it's one of those Pandora's box thing. You just imagine that you make a model of an exoplanet, or imagine you get data from the Hubble Space Telescope like I showed you, and you want to fit the data, but the data is not that good. So you can imagine running like 10 million models, 100 million models, 1 billion models. And then whichever ones fit the data, that constrains the identification and the amount of gases that are there. Only your computer doesn't have time to run millions or billions of models. So you have to do something a bit more clever. You have to walk through parameter space in a more clever way with some prior information. And so now it's kind of like gold standard in the field to use these retrieval techniques. Only usually our data is not quite good enough for it. Even our molecular line lists and cross sections don't really warrant it. So we got ourselves in a bit of a tangle here, but I just wanted you to know that it's kind of complicated. I had to give my talk at a fairly high level, so I wanted you to see this detail. And just for a bit more detail, one of my students tried to help come up with a way that we could sort through these thousands of molecules. We can't study them one by one. Instead, we will study them according to their so-called functional group. But essentially, he's saying we start with the databases I was talking about. We see if they have spectra, which out of those 14,000 molecules, honestly, like only 500 of them have cross-sections that exist. Then we put it through a forward model of an exoplanet atmosphere, making different assumptions for different scenarios of what the composition of that atmosphere might be. Then we figure out whether the molecule should be evaluated. It has to be have a unique set of spectral features and other criteria. The main thing is can the molecule accumulate in an atmosphere? Can it survive atmosphere chemistry? Often it's no, so we drop that. If it's yes, that's good news. And Can it survive photochemistry? If it's yes, it's good news. And it's even more of a bonus if it's somehow related to life on Earth. So anyway, the molecule I just wanted to tell you about today, this is the very last part of my talk, because there are those 14,000 molecules that we classify, but one set of them is phosphine. And phosphine, I wanted to educate you all on phosphine as a biosignature gas. Oddly enough, phosphine appeared in our list of molecules that appear to be rarely or never made by life. It's actually an essential element for all life on Earth, but it doesn't seem to be something that life makes. Phosphine anyway. And some of you probably don't know this factoid, but phosphine is incredibly toxic. We humans do make it for mostly pesticides. It was also used as a chemical warfare agent in World War I. So people argue against phosphine as a biosignature gas, that it's so toxic and unstable. It's not really produced by life, but we actually wrote a series of papers, and William Baines is my other biochemistry colleague I was talking about. And he wrote a paper arguing against these arguments, saying that actually phosphine is only toxic and unstable in oxidized environments. And you may not be surprised the kind of obscure things you can find in the literature, but people had done some tests on insects where they made the insect dormant. So it wasn't metabolizing. The insect was not using oxygen. And they flooded it with phosphine. And then later they made it back to the normal atmosphere. They revived the insects and they were totally fine. So the phosphine didn't kill them because it wasn't binding to things related to oxygen. Now the second argument also goes away, no confirmed life-producing instances. It turns out that there's very strong evidence that life produces phosphine. People have taken mixed cultures of bacteria in the lab and they've measured phosphine coming off of the bacteria. And also people find phosphine in other environments. Many animals produce it, it's produced in their feces. So there is a lot in the environment. There's like sludges and wetlands where there is phosphine being measured. So my team actually, it's like each student or postdoc is getting a gas to study and to search the literature and understand. Well, in this case, we had William Baines do it, and Janusz Petkowski, we try to do like a holistic picture of the gas. Can it accumulate in an atmosphere given photochemistry? Can it be observed with the James Webb Space Telescope? And is there any connection to life on Earth? So this is a bit busy, so I won't go through it all in detail. It's just to prove to you that we actually simulate exoplanet atmospheres. And this is showing you the transit depth. If you have time to look at the numbers, they're absolutely tiny. This is wavelength in microns. And these giant white features are showing you phosphine. And the gray is the same atmosphere without phosphine. Phosphine can accumulate in an atmosphere that has no oxygen. So if we imagine like a carbon dioxide atmosphere or a hydrogen atmosphere, why we love phosphine as a biosignature gas is there's no false positive. It's incredibly hard to make it thermodynamically. Nature doesn't want to make phosphine. The bad news is that we need huge rates. Honestly, I told you it comes in feces. You'd have to have like a sewage plant covering your entire planet to generate enough phosphine. So I wanted to share that story of phosphine. If there's only one thing you can remember from my talk, just remember phosphine is associated with life. It could be a biosignature gas. And what we've started to find is that most of the gases we studied, they have to have very large production rates. Furthermore, for most of them, it's starting to look like, just like those cyanobacteria re-engineered our atmosphere. That for us to hope to detect these signs of life in the near future, we have to have a kind of life that, for whatever reason, produced a ton of phosphine or some of these other gases we've been studying. And many of these gases, in order to re-engineer the atmosphere, the life actually has to produce the gas in a higher rate than the destructive molecules are being produced by photochemistry. So this is like the very latest. You won't hear this probably anywhere else. We're still kind of trying to understand what is all this meaning. I don't want to keep putting my students and postdocs on individual gases if it's all going to be the same answer. So we'll see where this goes. So to summarize my talk, there are thousands of exoplanets that we know, and small rocky exoplanets are established to be common. The next generation of telescopes, both the James Webb Space Telescope and the large ground-based telescopes under construction, and our very sophisticated space telescopes, including Starshade that we're designing, each of those has the capability of observing atmospheres of small planets for water vapor and for biosignature gases. I gave you like the tiniest glimpse into my research in chemical space, where in searching for biosignature gases, we also uncovered this, hopefully it's not still a crazy theory, I promise, about molecules that aren't produced by life, and those actually may lead us into insight into origin and evolution of life. And I'd like to thank my colleagues who have worked on this work, and to thank my sponsors, and to thank all of you for being a great audience. And I can tell that only by all the questions that you've asked. And I'll now look forward to answering some of those questions. Thank you.
Thank you so much, Sarah. This was wonderful. We have, as you probably have seen, a flood of questions in the Q&A window, and all like digging much deeper into all the details that you showed us here in your wonderful talk. Thank you so much. I'm gonna start with the first question that sort of continues the line of argumentation that you pitched in the last part of your talk. What about industrial gases, right? What about not only looking for biosignatures, but actually technosignatures in a way?
Yes, that's a good question. And technosignatures are definitely a topic people have researched. You have to ask yourself this after the last slide: the industrial gases we've produced, have they re-engineered our atmosphere? And the answer is they haven't. And it turns out that even the chlorofluorocarbons that made our ozone hole, those are still very narrow features in the spectrum. And they're still there in very tiny quantities. And at least in the next few decades, we won't have the capability to spot those. We won't be able to see those now. But this field is going to go on for 100 years, 200 years. So surely in the very far future, that will be something people can look for, but not right now.
So we have many questions from the Q&A, as I'm sure you've seen. So let's go to the top of the Q&A. So from Felipe Gonzalez, how much can we constrain the interior structure of exoplanets, and how much can we infer from it?
Right. So we have a measurement of mass and size for a lot of planets, and that gives us an average density. So we can infer what the interior is made of if it falls into two extremes. If it's a very low density planet, we know that it either must have like a volatile envelope, like hydrogen, helium, or it could have a large fraction of water, which is a really low dense material. If the planet is very high density, it's got to have a lot of iron in it. Now that's not that satisfying, because that's kind of where we're at. In the field of exoplanets, our data is limited, but we can still make models, and I could give you the range of possibilities of interior composition for a given planet. But each planet doesn't, unfortunately, have a unique description of its interior.
Okay, the next question is from, things are jumping around, from Alfredo Navarrete. It's in Spanish, but I have a translation here. What is the use of looking for exoplanets similar to Earth? Because if we wanted to go towards them with current technology, we would arrive in 1,000 years.
Yes, so by the way, that is actually the question I get asked most often from any audience of any kind. It's, can we go there? And if we can't go there, because the questioner knows that, why are we doing this? Well, let's just say that for now, it has to be satisfying enough to study those planets from afar, just to know that there's a planet like Earth out there. And I really get that that's not enough. So I do want to say something a little out there in response to that question. Basically, in exoplanets, the line between what is considered mainstream science and what is considered completely crazy, that line is constantly shifting. Like in my talk, I could only see the panelists, and nobody laughed when I mentioned starshade. But do you realize that when we started our first study of this in around 2013, when I would tell my friends at the barbecue or my colleagues, they'd be like, starshade, what? That thing's dead. Like, why would you do that? Formation flying at the precision you require between the Space Telescope and the starshade, that is impossible. But now people take it seriously, actually. So I won't be the one to say that we're going to travel there, but I will say there's an activity going on that has moved the line. So it's less of a giggle factor. And that project is called Starshot. And Starshot isn't going to send us humans there, but it's a $100 million injection, which won't make it happen, but it will make it, technology advance, to send thousands of little tiny spaceships that will have like a solar sail, and we'll have a giant laser bank on Earth that will blast them. You can laugh at this if you want, but that will blast these little sails and accelerate them to 1/20th the speed of light, so that some of these sails, not all of them will make it, that some will survive the journey past Alpha Centauri, they'll make it in 20 years. Not thousands, but that's 20 years. They'll snap a few photos, transmit those photos back. Like, honestly, that can happen in the next century. Like, it's not going to happen in our lifetime, but we hope that that plants the seed for some way. You know, maybe we're not going to like hibernate on a spaceship. Maybe, you know, in 1,000 years, we'll send our raw biological material and, you know, instructions for creating us. Now we're going to get into science fiction, so we can't go right now. And yeah, we'll see what happens.
So actually connected to Starshade, there was a question further down from Doug Giesler. How would the oblateness how would the star's oblateness affect the Starshade performance?
The oblateness shouldn't be a problem. It's really, as long as the star, let me think. That is a good question though. I have to admit, I haven't heard that one before, but I think the oblateness is not a problem because the oblateness of the star is not very big actually. So I think that's fine. Now, if you were to ask, are there binary stars? We can't deal with 2 binary stars with the Starshade yet, but 1 star on its own is probably fine.
Okay, so let's go back to the Q&A, back to the top. We have a question from Rubiat Khan. Why do we tend to search for life on exoplanets according to how life appeared and evolved on Earth? Could life appear from other gases on those exoplanets?
Yes, well, the point is that we're not really making any assumptions about life on Earth or life elsewhere. We're simply actually trying to look for a gas that doesn't belong, that is there in such huge quantities where it doesn't belong. And I must have forgot to like make this really clear, but in trying to list all the molecules that could be in gas form at room temperature and pressure, I'm also including gases that are not made by life on Earth. So we do wish to investigate all gases, and we're looking for gases that are in an unusual quantity or somehow don't fit in with the other gases in the atmosphere. The only assumption we're making, by the way, is that like life on Earth, life elsewhere will use chemistry to extract energy from the environment, to store energy, and to metabolize and give off waste gases. Like we could imagine there's mechanical life, like a windmill, that somehow just generates energy mechanically and there's no chemistry involved. So we're not assuming anything about life on Earth. As astronomers, we are limited to spectroscopy, and we're limited to believing that life uses chemistry.
Okay, so the next question. We have a question from Stephen Ridgway. If we have a fixed funding available to invest in this effort, how would it be optimally distributed in time?
Good question. Okay, that actually might be the best question. No, kind of a political question. You know, I think I would invest it in a way so that the momentum and the excitement keeps moving along. You know, if we only invest in HabEx or LUVOIR, that is still so far away. We won't have enough to sort of feed our souls, so to speak. So even though I like M-STARS, I don't love them, but I would fund this initial search for life, most of it on what we can do now, what is available to us today. And I'd put a smaller amount in keeping the technology moving towards for the future.
There is another great question here from Swastik Chobai in the Q&A. Does the planetary atmosphere have any dependence on the initial formation stages of, I guess, the planetary system, the environment, and does tracing the planetary atmosphere can give us any information about the earlier stages of the formation process in the galactic environment, I guess?
Right.
And if so, how this will help us study the early stages of the solar system formation and what might have led to the formation of life in general?
Yeah, there's about 5 questions there, but I'll answer.
Yes.
So giant planets like Jupiter retain their primitive atmospheres and the gases they were born with. And so we're hoping that as we can study more giant planets, that we can measure their so-called metallicity. And that may tell us a lot, actually, because our solar system, Jupiter, Saturn, Uranus, and Neptune, they get more and more metal rich as you go out. They have more heavier elements. We're not totally sure why that is. We think it's the composition of the disk, but if we can see those patterns in other systems, we could learn more about what that has to do with their formation there. And that applies to the second part of the question about the atmospheres related to the protoplanetary disk. I don't know if it's going to help us understand the formation of life on Earth yet. for rocky planets, our Earth has a secondary or even a tertiary atmosphere. We think we had a lot of hydrogen in our atmosphere initially that escaped. We think we had a lot of carbon dioxide that went into our ocean. Then, of course, we got oxygen later. So for the terrestrial planets, it'll be quite hard to, work our way back.
Conrad has raised his hand.
Yes, so I'm going to ask, because I also find it very interesting, the question from Leticia Carvalho. What actually changes between the habitability of planets around binary and multiple systems? And among the candidates that you have studied, are there any planets around triple systems or higher orders, so with more stars?
So right now, very little studies have been done on planets orbiting binary stars and triple systems, but usually the effect isn't as dramatic as you think. In order to be stable, the planet has to, if it's orbiting two stars, it has to be, somewhat far from those stars. So the two stars don't act as one, but they may as well be somewhat close to that. You might have a very long daytime, for example, but the energy arguments don't destroy you. In terms of triple systems, most triple star systems are hierarchical. So you have two orbiting each other, then you have the third one in a wider orbit, and we have that. Proxima Centauri is the triple with the Alpha Centauri system. And so usually in that case, the two stars are too far away to really make a difference. So it hasn't been studied much, but the few studies that have been done don't show any dramatic effects.
So Sarankana has raised her hand.
Hi, Sarah. Thank you for the talk. I am personally interested in oxygen detection, and I know that we are still limited by the instrument sensitivity. But let's say within the 20 years time frame, how would you filter out to get the best candidate of planet to look for this signature? Either it's oxygen or phosphine.
And there's many other gases too. So how we filter out the planets? Well, in the shorter term, in the next 20 years, believe it or not, nature has pretty much filtered for us. We're not going to have thousands of planets. I wish we could have, that would be a great problem to have. But so for the James Webb Space Telescope, when we're thinking about habitable worlds, maybe there'll be 6 candidates to choose from. We might have to narrow that down to 3, but it's typically which ones are, the easiest to observe. That'll probably be what makes it happen. When we can launch in 20 years, if we're lucky and we got a HabEx to launch, we'd be able to survey about 100 stars. And each of the planets we found, we would be able to look for oxygen. Yeah, so nature gave us too few ones to have to choose. We just have to keep our fingers crossed that oxygen is being generated on one of these planets.
So Dennis also raised his hand. You're muted, Dennis.
Thank you, Sarah, for a very interesting talk. Fascinating. I have a question about star shade and how accurately it needs to be positioned. So when I think about the pointing accuracy of Hubble or JWST, if I think of star shade as pointing in a direction, does it have to be pointed to about the same accuracy and stability as Hubble?
Well, okay, I don't think I can do that translation in my head right now, but I can tell you how it has to be positioned. Like Starshade has to line up with that telescope I could probably do this calculation. I probably can't do the calculation, but it has to be lined up incredibly precisely. So, but it's not so much pointing because it has a closed loop control system. Like Starshade will have an LED and a laser that shine at the telescope so that when it's lining up, it knows it's heading in the right direction. And once Starshade locks on with the telescope, red light leakage around the edges that's not used for science, like it'll only have this very special pattern of red light leaking around the edges. It will know it's locked into place. But it has to be lined up vertically, like it's going to be tens of thousands of kilometers apart, and it has to be within a few hundred kilometers this way. It's actually the lateral direction that's very tricky. It has to be to within a few meters. It has to line itself up to within a few meters.
Okay, thank you.
Okay, if we go back to the top of the Q&A, we have a question from Giovannina Manser. can you discuss if you can make any alterations to the Drake equation and the probability of us detecting an exoplanet with biosignature gases one day?
Yes, actually. In fact, I did that revision. And I actually asked Frank Drake, I saw him he had like an 80th birthday. I think it was his 80th birthday. And he flew here to Massachusetts. And they had this special panel discussion where each person got to represent one term in the Great Drake equation. And I asked him if he minded if I took his equation and reworked it. Because the Drake equation itself is for the radio search for a message intentionally sent from intelligent civilization. So I reworked the equation. You can find it on a website somewhere. There is a slight error though with whoever put the website together. But just like the Drake equation, it's not really predictive. The equation's meant to illustrate the different factors involved. And we don't know all the answers to all the factors. So yes, you can rewrite the Drake equation. And if you search for the so-called Seeger equation, it's not really a real equation. I like to call it the revised Drake equation. You can look into it a little more.
So we have another question from Isaias Rojas. So it's in Spanish, so again, I've got a translation. Are the planets' orbital planes really random? Isn't there a preferential orbit for the interaction with the galaxy disk?
Great question. That's a very nice question. So there's not really any interaction with the galaxy disk. Like, when stars form, they're forming from a 3D ball of gas and dust, and they collapse. But the way they collapse is truly random. Now, there is actually a study on exoplanets, because if it's truly random, then we should see the number of transits expected compared to the number of planets we know altogether that don't show transits, if you will. And so we don't really have enough to say yes or no, but the evidence is looking like that they're all random.
So Katerina has also identified a question.
Yes. So thank you a lot, Sarah, for a very nice talk. And I have another question actually from Stephen Ridgway. So would you encourage a major effort to study the Proxima system, even if the effort did not really apply to more distant targets?
Yes, I would. So, okay, in exoplanets now, we have had an embarrassment of riches. I don't know if you have that same phrase in Spanish, but it means like we're just so lucky and blessed to have, wow. The Kepler Space Telescope found thousands of planets. The TESS mission, we're finding 100 new planet candidates a month. We're very busy finding planets. It's a job. It's like a real job now. We have to hire extra people. Well, we can't hire. We've got a hiring freeze now because of coronavirus, but sometimes you just don't have enough people to find all the planets. So we're going to slowly have to shift our paradigm. Instead of finding so many planets and knowing so very little about them, we really do need to shift our focus to study individual planets in a lot of detail. Now, this is a bit of a problem because there won't really be enough data to go around to all astronomers. But it really, I think, is it's a good question. I'm glad that Stephen Ridgway asked it so I could talk a bit about this, but we're going to see that. I mentioned Starshade Probe. I have to keep pushing for it, of course. We'll look at our 12 nearest, brightest sun-like stars. We might only even do 8. Like, that's nothing compared to thousands of planets that Kepler found. So it is time to return to individual objects, the very nearest stars, including Proxima, and study them in a lot of detail.
Okay, so I've got 2 more questions I've picked out from the Q&A. So there's another one from Giovannina Manser. Do you think there's a possibility of finding life on exomoons? What are some ways exoplanet life could be influenced by orbiting a planet rather than a star? And how far away are humans from being able to search for this kind of life?
Well, from my talk, hopefully you gathered that we're still quite far from searching for signs of life on exoplanets. The James Webb Space Telescope will be our first chance. And I might not have been honest enough because if we make an assumption that the James Webb has a 10 part per million floor, it makes it very hard to study rocky planets with thin atmospheres like our Earth. So moons are a whole other story. We haven't found we have no robust findings of moons on exoplanets now. Earth itself is very small, and a moon is even smaller. And that moon is not just next to the planet, but that the moon and planet are next to the star. So moons just aren't a great thing from the observational astronomy perspective right now. Certainly they could have life on them, but the signal from the moon will be dwarfed by the planet.
Okay. And the final question is from Debbie McKay. Can tidally locked exoplanets have liquid oceans on their dark side, and would such a planet be habitable?
Yes, well, the funny thing was, a while back, before M-stars became kind of the thing, people didn't like M-stars for life. And one of the main reasons was what the questioner asked, was that if it's hot on one side and cold on the other, surely that's bad for life. But what we found now is that through models of atmosphere circulation, whereby, I'm not sure how cold it is there in Chile, but here in Massachusetts, and where some of us are from in Canada, like on a cold winter day, when you open your front door, all that cold air rushes in and the hot air rushes out. I can just remember being a child and my parents yelling at me to like close the door. Well, on the planet, it is hot on one side, but if there's an atmosphere that's more massive than Mars's atmosphere, and Mars has a pretty thin atmosphere, then the energy will get circulated. The heat wants to go where it's cold on the whole. And so we think for most of these tidally locked planets, it's really not a problem because the energy will be moved around the planet.
Okay, so with the help of all the panel, we've identified quite a few questions that we've asked from the Q&A. So I'd like to send you these questions for consideration for the prize. While I do that, does anyone else on the panel have a question? Okay.
There is actually one question here that is really interesting. So, given the star formation history in our galaxy and all across the universe, it's related to a question also by Debbie McKay. Are more exoplanets found around maybe remnants that we should be looking at? Stellar remnants.
Stellar, like white dwarfs, you mean?
White dwarfs, pulsars, exploring those worlds.
Yes, actually, people do look for planets around white dwarfs, and they've been finding some interesting things. There are not a lot of white dwarfs that are really quite bright enough to do this. So it's tricky.
It's tricky.
I'm reading through the questions right now, so.
You've got the link in the chat, yeah?
There are many great questions in the Q&A.
Yeah, there's so many great questions.
Yeah, I'd like to say thank you again to the panel for helping me select the questions. So many were coming in, it was hard to read them.
Let's see. Okay, this is a little, okay, there's just really, yeah, it's definitely hard to choose because there's so many good questions. Okay, so the question I actually liked the best, believe it or not, was the question about whether the planets are truly randomly distributed or not. That was I think that was the best question that I got today, actually. And one of the reasons I thought it was the best question was because we often don't challenge assumptions. Like we're often just like, okay, let's just kind of, yeah, that's what the professor said, so it's true. But I think pushing on that and asking like if there is evidence, I really like that one the best. I also did really like the one about what would we pay for, but I felt that one was like more of a political one and not really as much in the true spirit of science as the one I picked. So thank you everyone for all of those great questions. It was really hard to choose.
Okay, so that question I believe was asked by Isaias Rojas. Are the planets' orbits really random, and isn't there a preferential orientation for the interaction of the galaxy disk? Is that correct? Yeah. Okay, so congratulations to Isaias. We will be in contact with you via email to discuss delivery of the prize.
John has another question.
Yeah.
Okay.
Yeah, so there was a couple questions along this line, so I thought I would just raise it. So it's more of like speculating, like what would be the, if we did detect some signature of life on another planet, what would be the next steps, or what speculate on what you think the reactions would be?
Okay, so first of all, my best guess is when we find this, okay, so what I tell my team is I want to be like the LIGO people. When LIGO made a discovery of a gravitational wave, it was wow. I mean, it was so clear, it was really irrefutable. I'm afraid instead we're not going to be that. We're going to be the noisy data that you have to really overanalyze and remove systematics in such a way that you might even be introducing a signal. So I don't think our signal will be like out there super strong. So initially it's not going to be like, yes, we found life. It's going to be, wow, we have this signal, it's pretty strong. We need to do more. So it's kind of a boring answer, but I think the next thing we need to do is build a more capable telescope. And I think we'll need to ramp up the crazy ideas out there on the other side of the line of between crazy and mainstream to figure out a way to send a probe there. There's one more idea I'll mention to you that as an example of something we could invest in. And this is the so-called gravitational lens telescope. People have thought about using our sun as a gravitational lens. And we'd have to send a telescope to 500 astronomical units. So 500 times the Earth-Sun distance. Now there's sort of there could be some showstoppers in there. We'd have to slingshot by the sun, so close to it. We'd need a very special heat shield in order to help accelerate. It would still take a long time, a decade or two to get to that spot. And we'd have to line up in a really special way, also blocking out our sunlight. And we would line up with a distant planet that we have to know is there. And we could literally resolve the surface to like a kilometer, or I don't know, 10 or 100 kilometers, and we could get much more detailed information. So we'd have to find a way to get better data and hopefully invest in a way to go there.
Okay, I think we're going to wrap this up. Thank you so much, everyone, for joining us today. This was an exciting talk. There is such a bright future ahead for this field. Thank you, Sarah, for your time and for telling us about the science and your projects and your thoughts also for the future. So everything will be recorded. We will put this on the Astrofísica UC YouTube channel, of course, again in English and Spanish, and with higher quality than the live stream. Our next scheduled talk will be on the 11th of September by Mike Merrifield, who will be telling us about observations of nearby galaxies, not just beautiful, but also a key to their formation. And so there is nothing left to say except for thanking you all again. Thank you, Sarah. Thank you, panelists. And thank you, audience, for sticking with us. Stay safe, stay healthy, and stay happy. See you soon.